What if the ground under your feet is riding on a giant, slow-moving puzzle piece? Think about that for a second. You go outside, you look at the dirt or the street, and it feels completely still. But actually, that ground is moving, so slowly you can't even feel it. Over millions of years, this invisible movement can lift massive mountains right up into the sky, crack continents apart, and literally help volcanoes build brand new land. Okay, let's figure out how this works. To see how this works, we need to understand what our planet is actually made of. You see, Earth isn't just one solid ball of rock. It's built in layers, and the very top layer is hiding an absolutely massive, world-shaking secret. First up, let's peel back the planet and look inside Earth's puzzle layers. To understand these giant puzzle pieces, we have to look deep, deep inside the Earth. Think of our planet kind of like a hard-boiled egg, but, way hotter and a lot more complicated. Right on the outside, we've got the crust. That's the super thin, rocky layer where we live, where all the oceans and mountains sit. Right under that is the mantle, which is this massive, incredibly thick layer of hot, solid rock. Go even deeper and you hit the outer core, made entirely of liquid metal. And finally, smack in the center, there's the inner core, a giant ball of solid metal. It is absolutely wild to think about the massive scale of what's right beneath our feet. Now, the part we really care about right now is called the lithosphere. Basically, the thin crust and the very top, coolest part of the mantle stick together to make this stiff outer shell. But here's the huge secret. That shell is not just one solid, smooth piece. It's actually completely shattered into gigantic slabs of rock called tectonic plates. Some plates are carrying entire continents, some are holding the bottom of deep oceans, and some carry both. These are the giant puzzle pieces covering our whole planet. So why does the puzzle move? Well, slow and steady wins the race. If the Earth is totally covered in these huge puzzle pieces, what's actually making them shift around? First, we have got to bust a major myth. A lot of people think these giant rock plates are just floating around on a sloshing underground ocean of liquid lava. No way, that's totally a myth. The fact is, plates ride right on top of the mantle, and the mantle is hot, solid rock. But because it is so intensely hot down there over a very, very long time, that solid rock can slowly bend, deform, and flow. It's kind of like a cracked chocolate shell sitting on top of warm, gooey caramel. They shift and bump into each other. Except, Earth's plates are solid rock, not chocolate. And when we say they move slowly, we mean incredibly slowly. We are literally talking about a tiny movement of just a few centimeters per year. That is about as fast as your fingernails grow. Crazy, right? It totally doesn't seem like much, but when you add up those tiny fingernail-sized movements over millions and millions of years, the results are powerful enough to change the world. So what's the engine driving all of this? Heat! Deep inside the Earth, hot material in the mantle slowly rises, cools off near the top, and then sinks right back down. This slow churning motion is called convection. And on top of that, some of the really dense, heavy ocean plates actually sink back down into the mantle, and as they go, they literally pull the rest of the puzzle piece along behind them. It's a completely unstoppable slow-motion engine. Now for the fun part, when puzzle pieces meet. This is where all the action happens at the edges. Because Earth's puzzle pieces are constantly moving around, they are eventually going to bump into each other. And right at those edges, where these giant plates actually meet, is where the most dramatic geology on the planet happens. We're talking mountains rising and the land cracking open. There are basically three main ways these plates interact. Divergent boundaries are where plates pull apart, kind of like at the Mid-Atlantic Ridge. Convergent boundaries are where plates crash right into each other, creating massive mountains like the Himalayas. And transform boundaries are where plates slide past each other, just like the famous San Andreas Fault. Let's look at each of these real-world examples up close. First up, divergent boundaries. This is where plates are actively moving away from each other. As they pull apart, hot rock rises up from below, cools off, and boom, brand new crust is born. This actually happens a lot deep underwater at mid-ocean ridges. For example, the entire Atlantic Ocean is actually getting wider every single year because the plates are pulling apart. Just imagine slowly pulling a piece of warm bread dough apart until a crack opens up in the middle and new dough pushes up from the inside. That's exactly what the Earth is doing here. On land, this exact same process can even form massive rift valleys. Next, we have convergent boundaries. This is where plates crash together. Imagine pushing two heavy rugs together on the floor. They don't sink down into the floor, right? They crumple and wrinkle upward. That is exactly what happens when two thick continental plates collide. Neither one wants to sink, so they just crumple upward to build absolutely massive mountain ranges. In fact, the mighty Himalayas were formed, and get this, are still rising higher today because the Indian plate is actively crashing right into the Eurasian plate. But wait, what happens when a thinner ocean plate crashes into a thick continental plate? Well, the ocean plate is a lot denser and heavier, so it actually dives straight beneath the continent. This amazing process is called subduction. As that heavy plate slides underneath and sinks deep into the incredibly hot mantle, it helps create magma. And that magma, it can eventually rise all the way up to the surface and feed volcanoes. The super tall Andes Mountains in South America are a perfect example of this subduction process in action right now. Our third type is the transform boundary. This is where plates are just trying to slide sideways past each other. But here's the trick. They don't glide smoothly at all. The edges of these rock plates are incredibly rough and jagged, so they often lock up and get completely stuck. The plates themselves are still trying to move, though, so stress just builds up on the rocks. It builds and builds and builds until suddenly, slip! That sudden slip instantly releases a massive amount of energy, and we feel that energy rolling through the ground as an earthquake. Now, earthquakes can definitely seem a little scary, but remember, Earth isn't trying to destroy anything. This is just a totally natural process that has been shaping our home for billions of years. Plus, the really great news is that scientists and engineers study these sudden slips incredibly closely. Understanding exactly how they work helps us design much safer buildings and keeps our communities prepared and protected. Which brings us to the glowing ring of fire, a massive horseshoe of geological action. When we map out exactly where all these plate boundaries and subduction zones actually are, a massive crystal-clear pattern emerges. This is the famous Ring of Fire. It's a huge horseshoe-shaped zone circling the Pacific Ocean that's just packed with active boundaries. Because there's so much plate collision and subduction going on here, it is highly active with huge earthquakes and fiery volcanoes. I mean, just look at the places sitting right on this glowing rim. You've got Japan, Indonesia, the Philippines, New Zealand, Alaska, and all along the west coasts of North and South America. But hey, nature always has a few surprises up its sleeve. While most of the action happens right at the edges of the puzzle pieces, that's not always the case. Sometimes volcanoes can pop up right in the middle of a plate. We call these hotspots. Basically, extremely hot rock rises from deep inside an isolated part of the mantle and punches right through the crust like a blowtorch. This forms places like the beautiful Hawaiian Islands, which are sitting completely away from any plate boundaries. Okay, let's talk about clues from the past. How do we actually know all this? If this entire puzzle moves so incredibly slowly, how did scientists ever figure it out in the first place? Well, scientists like Alfred Wegener started putting together an amazing evidence checklist. First, just look at a map. Continents like South America and Africa look like they perfectly fit together, right? Second, they actually found matching dinosaur fossils and rock layers on continents that are now separated by giant oceans. How else could they get there? Later on, scientists discovered literal stripes of magnetic minerals on the ocean floor that proved brand new crust was constantly forming. And today, we literally use high-tech GPS satellites up in space to track these massive puzzle pieces moving centimeter by tiny centimeter. Finally, why does Earth's puzzle matter? Well, it's all about shaping our home. Learning about plate tectonics is absolutely crucial because it helps us understand the spectacular landscapes we live on, the volcanoes and earthquakes we experience, and the long, amazing story of Earth itself. It teaches us how to find minerals, map deep oceans, and most importantly, prepare our communities for these massive natural forces. So the next time you see a mountain reaching into the clouds, a towering volcano, a map of the deep ocean floor, or even just a tiny crack in the sidewalk, remember that Earth is not a frozen statue. It is a vibrant, active planet. Earth's slow-moving puzzle pieces write giant stories in rock. The ground beneath you holds billions of years of history, just waiting to be uncovered. So what story will you discover next?